Hello friends, I am Professor A.K.chaubey, retired as Professor and Department Head from Aligarh Muslim University, Aligarh. After retirement in November 2004, I left India and joined Addis Ababa University, Ethiopia as Professor in Nuclear Physics. Friends, I have about 59 years of teaching and research experience. I started my teaching career in 1963, July 1963 from DS College, Aligarh. And then I left after 6 months to join research and became a staff member in the Aligarh Muslim University, Aligarh, and retired in 2004. So that way I have a lot of experience of teaching nuclear physics, teaching all other branches of physics, and particularly higher MSc and PhD classes in nuclear physics. For 17 years in Ethiopia, I was teaching MSc in nuclear physics and PhD in nuclear physics courses. And I have produced more than 55 MScs in nuclear physics and about 16 PhDs already got PhD degree in Ethiopia. Ethiopian students, there was nothing in Ethiopia. There was no research environment, there was no much equipment, and there was no nuclear physics professor. Still there is no nuclear professor in Ethiopia. I was the only one. Then one more appointed, he left after 2-3 years. So friends, I have started after returning from Ethiopia. Now I am finally back. I have started making videos on astrological things which I was having interest in my young age. I am making video series as Ganpati Watch Astrology, Professor A.k.chaubey, and you might have watched many videos on astrological problems. Now I want to start some teaching in physics. Under the heading, I will have Physics Made Simple. I want to explain you physical phenomena. I will not be deriving mathematical equations. I want to explain you physical phenomena in terms of physics. What is the physics behind the mathematical expression? So I start as taking some programs on physics teaching under the heading Physics Made Simple. I will talk about all the nuclear physics important topics and radiations, radiation detectors, nuclear reactions, nuclear forces, accelerators, etc. Everything important topic I will try to cover in my lectures on Physics Made Simple. Okay, so let us talk about the gamma ray interaction with matter. Gamma ray interaction with matter. So first let us have gamma ray. How to differentiate gamma rays? Gamma rays are electromagnetic radiations. These are energy quanta. We started from energy quanta, quantum physics, Planck's quantum idea from the Bohr's theory that emission of radiation is not continuous. It is discrete energy in the form of some energy particles. That is the wave theory and particle theory. So energy particles, you can say, or having wave nature, both dual nature. So quanta, energy quanta. Energy quanta, E is equal to h nu, from where quantum theory of physics started. Wherever we find h in the formula, that becomes quantum. So E is equal to h nu, nu is the frequency, and h the Planck constant, or E is equal to written as hc over lambda in terms of wavelength. H is the Planck constant and c is the light velocity. So energy quanta is written as hc over lambda. Lambda is the associated wavelength with each particle. So that way, early started from photon. Photon was visible light. Visible, then ultraviolet. That is the energy increasing. So energy increasing means you have X-rays, then you have gamma rays. So in fact, gamma rays are nothing special, but energy quanta of high energy means you have photons in the EV region, you have KEV region, that is a kilo electron volt, to MEV region, that is the gamma. E gamma is equal to hc over lambda, and this lambda will be different for different energy. For example, I have suppose I put the value of H and C and write this expression in terms of a numerical value. I have 1, 2, 1, 2, 4, 1, 2, 4, 1, 2.5. This is EV, electron volt over lambda. The expression of energy in terms of putting by this value of SC, etc., and converting this joules into the electron volt, you can have this much lambda. It means as lambda changes, energy, lambda increases, energy decreases, or lambda decreases, energy increases. So that way you can find out lambda. If it is, you have say for E is equal to about 10 to power 4, E is equal to about 10 to power 4 electron volt. You can calculate from this lambda is of the order of, the value of lambda is about 1.24 angstrom. For E is equal to 10 to power 5 electron volt, the value of lambda is about, decreases, means 0.124 angstrom. For E is equal to 10 to the power 6 electron volt, lambda further decreases to 0.01. So means the value of lambda as the energy increases goes down, or frequency increases. So these KEV, this EV means 10 to the power EV means 1000, 10 to the power 3 means 1000. So 10 KEV, 10 to the power 6 means MEV, 1 MEV, 10 to the power 2 KEV, like that. So as the energy for gamma rays are generally few MeV and few hundred keV also. Less than this, there are X-rays, maybe keVs, and then you have on the side other radiations which are, say, visible or optical. Optical means visible and red, infrared, and on other side blue, violet, ultraviolet, etc. So we have gamma radiations which are having high energy, maybe few MeV or hundreds of keV. These radiations, in other words, they are also called electromagnetic radiations. But the difference is that gamma rays are, you may have electromagnetic radiation nature from some other source of this energy, but gamma rays are of nuclear origin. The other radiations, optical and X-rays also, they are from atomic origin. X-rays are to, say, 80, from lead we have about 80 keV, etc. So X-rays of few tens of keVs, they are from atomic de-excitation. Gamma rays are produced from nuclear de-excitation, means when the excited state of nucleus is going to the ground state, we say that a nuclear energy state coming down to zero energy, this having E energy, and this coming down de-excites by emission of a gamma, E gamma equal to E. The energy difference. So nuclear de-excitation. Nuclear de-excitation. The nuclear de-excitation is the source for gamma ray produced by and X-rays and optical, we read in the Morse theory, Balmer series, Lemon series, Pund series, etc. Those radiations are optical radiations, visible or ultraviolet, etc. Those are of atomic de-excitation. So the difference in the gamma ray is that they are high energy electromagnetic radiation, and the energy is such that you will not get the energy in the atomic de-excitation. These are due to the nuclear de-excitation. Okay? So we are interested in talking about the gamma ray interaction with matter. That is the main interaction. I will talk about the interactions which are used for the detection of gamma radiations. Means gamma ray attenuation means gamma ray when passing through matter, say this is any foil here, and gamma ray beam is coming from this side, and this is some thickness, say dx, and on this side we are having gamma ray. We know, we have one expression we have read many times, several times, that the I intensity I is equal to I naught e to power minus mu x. This is the expression which shows gamma ray attenuation. This is derived very easily, so I am not interested in derivation of formula. I want to explain physics. So this formula is that if x is equal to 0, that thickness of the observer, then intensity of gamma ray I is equal to I naught. That is I naught, x is equal to 0. And mu is known as, simply you can have, by definition, if I put I is equal to I naught by 2, half of this, and I say that x, where I becomes half, is I write by x half, I can get a simple, from this relation, by putting the value of I equal to I naught by 2 and x is equal to x by 1 by 2, I can get a relation that mu is equal to 0.693 divided by x half. This is the formula, just you have to put this here. This means that mu is related with the x half. X half means the thickness which will decrease the intensity by half. It makes the half of the initial intensity. So that thickness is related with mu. Mu is called the attenuation coefficient, absorption coefficient. In fact, mu is the total. Mu is the attenuation coefficient. Or we can write mu as mu AB plus mu scattering. That is, this is the mu for absorption of gamma ray. This is for scattering gamma ray. So gamma ray is being absorbed by the material and passes in forward direction, and gamma ray is scattered in all other directions. So coefficient for that. This shows the attenuation of beam by absorption. This shows the attenuation of beam by scattering. Total attenuation means mu. So this means that you have to add this. This mu is also called linear attenuation coefficient because here have I is equal to I naught e to power minus mu x. This can be written as simply, I can write this as simply I equal to I naught e to power minus mu over rho into rho x. This rho is the density. Rho is the density of material. So what do we get? This mu over rho is written by mu over rho is written as mu m, or it is called mass attenuation coefficient. Mass attenuation coefficient. And rho x can be replaced by xm. That is the thickness in mass unit. Means rho is the density, so kilogram per meter cube. Rho is kilogram per meter cube. X is meter. So this has got, xm has got dimension of xm units of kilogram per meter square. And you know mu x is the dimensionless. Mu is known, this is known mass attenuation coefficient, and this mu m, and you know mu over rho. Rho is the density, so its unit will be reverse of this. Mu m has dimensions of meter square per kilogram. So that mass attenuation coefficient actually depends. This is the mu is the called linear attenuation. Which is that this mu is the attenuation or mu AV absorption coefficient. If I write if n is, say n, if n is atoms per unit volume, that is the scattering centers. N is the scattering centers. How many? Scattering centers. Then you can write another symbol is sigma, is mu over n. Mu over n is defined as the sigma. Sigma is called cross section, attenuation, cross section. Because this will have the unit of area. You can see. You can find out n is the number of scattering centers. You can write n as simply n naught mass of the sample and A. A is the atomic number, atomic weight A, n naught is the Avogadro number. N is the Avogadro number. A is the atomic weight of the material, and m is the mass. So you can get, and you can get the mu you already know. units of you already know. So you can get the sigma. The sigma dimensions will be of area. That is a meter square. So sigma is known as, the name is given cross section, attenuation cross section, or absorption cross section, or scattering cross section. Sigma is sigma AB plus sigma SC. That is the absorption cross section. And this is the SC means scattering cross section. So friends, this is just about the attenuation. My aim is to explain the gamma ray interactions which are used for the experimental detection of the gamma, for the measurement of gamma energy, for the measurement of gamma intensity. We have three main interactions. There are many other also, but I will not talk them. The main interaction of gamma rays with metal R. One is called photoelectric effect. The other is called Compton effect. And third one is called pair production. These are the main three interactions which are used to detect gamma radiation in different energy regions. Some are important as the low energy region, some in the medium, and some in the high energy region. There are some other gamma ray interactions also which are not used for the detection of gamma radiation, just like Dalberg scattering, Thompson scattering, and there is one more important scattering which I will explain detailed in some two lectures. That is important. These are for the detection, for gamma detection. Another interaction important is known as the nuclear resonance scattering. Nuclear resonance scattering is another important. I will discuss this in detail because this gave birth to another important phenomena known as the Mossbauer effect. The Mossbauer effect is the outcome of nuclear resonance scattering. This is important phenomenon in solid state physics and has got a lot of application in chemistry, in astrophysics, in physics, in solid state physics, etc. So this nuclear resonance scattering I will talk separately in more detail because this gave birth to the important aspect of solid state physics which is now used. Earlier it was used in the nuclear physics for the measurement of lifetime of excited states. So this I will talk separately when we talk to the solid state application of Mossbauer effect also. But main interaction of gamma rays which are used for the detection of gamma radiation are, first I have already written here, first this was photoelectric. So what is photoelectric effect? How we understand? I will simply try to explain you the mathematics, and I will write mathematics, but explain the physics behind that. So what is the photoelectric effect? Just you know that you have a nucleus, you have atomic shells around the nucleus. A gamma ray is coming, say, here, it interacts with electrons sitting somewhere. Electrons are sitting in the atomic shell, say. These are electrons. So gamma ray interacting with, say, electron here. This is electron. This is the gamma ray. When gamma ray is interacting with the electron, what happens? This electron gets energy, and this electron is emitted with kinetic energy TE. Electron goes in certain direction. Means total gamma ray energy, total absorption of gamma ray energy, total absorption of gamma ray energy by atomic electron means gamma ray E gamma, that is h nu, comes towards the nucleus and it strikes, collides with the electron of atomic shell, and then this electron is emitted with some kinetic energy, TE, and some energy as the W is used to emit the electron, because electron is not free, electron is bound. So W is the binding energy of electron. Though this will be very small, few eV or very few keV, up to in heaviest elements maybe some 70-80 keV, but few eV. So mostly energy, as you know, most of the energy is taken by electron. So what we get in the photoelectric effect means photon is coming, photon of high energy is coming, and it strikes an atomic electron, and atomic electron is emitted with kinetic energy E. That we have some theoretical derivation of a formula for the, this is the photoelectric cross section, sigma pH. We write sigma pH is given by the theoretical quantum mechanics formula is that sigma E into sigma E into Z to power 5 and alpha to power 4 and 4 under root 2 and m naught c square over h cross omega to power 7 by 2. Yes. And this is, sigma, sigma E. Sigma E is defined as 8 pi r naught square, 8 pi r naught square over 3. This is called Thomson scattering cross section. And remember that this R naught is, R naught, R naught is equal to E square over 4 pi epsilon naught m naught c square This value is constant, about 2.8 into 10 to the power minus 50 meter. This is called a classical electron radius. Classical electron radius. Remember that we can have this sigma ph, which is the cross section for photoelectric effect derived quantum mechanically. This is the expression we can have that sigma ph in fact is equal to or proportional to z to power 5 and the sigma pH proportional to E gamma to power minus 7 by 2, because H cross omega is E gamma. E gamma is H cross omega energy. So this cross section for photoelectric effect is Z to power 5, means heavier elements more photoelectric effect, light elements very small. And energy, as the energy of gamma ray increases, the cross section for photoelectric effect decreases. In fact, you can get a curve like this, E gamma versus sigma pH or mu pH, mu photoelectric effect also. You can show this curve like coming down. This is a sigma pH. How mu pH or sigma pH? Both are possible. Then how the energy E gamma maybe some 0 or maybe say 500 and say 1 MeV, this is 500 keV, like that. So very soon this comes down. It is not 0, but it is exponentially going very, very small. So sigma pH or mu pH as energy, because theoretically we have, it is inversely proportional to energy power 7 by 2, and it is Z to power 5 proportional. So heavy element, more cross section. So sigma pH means photoelectric effect. What we have, E gamma is completely converted into electron of energy, some energy, kinetic energy of electron of energy, say dE. So this energy goes with the electron kinetic energy. So if you can count the electron with kinetic energy, you can have some information about the energy of the incoming radiation. And by detecting the emitted electron, by detecting the emitted electron, and by measuring its energy, gamma ray is identified. So we can identify gamma ray by detecting this emitted electron with kinetic energy. We measure the energy by some instrument. Somehow, we will explain later on, we measure the energy of the electron, and by detecting the electron, we can have an idea, oh, something has come which has produced this electron. Now there is an important question here, that I pose a question and you think for this. I tell you that the photoelectric effect the photoelectric effect takes place with most tightly bound electron, or photoelectric effect is mostly with K shell or K electron. You know there are shells we call divide K, L, M. K is the innermost nearest to the nucleus, then L shell, M shell, outer. So it doesn't take place. It doesn't take place with outermost or free electron. You will see that free electron, it becomes something else, some other effect. But why? What is the reason? It doesn't take place with outermost. Outermost electron is almost free because it has, nucleus has very small force effect. The Coulomb force is very small and it has least binding energy. So outermost electron is having least binding energy, innermost electron having highest binding energy, most tightly bound. So what is the reason photoelectric effect takes place with the most tightly bound electron? Think on this. What is the physics behind this? So I will try to explain you the physics. What is the photoelectric effect taking place? Photoelectric effect, we have a gamma ray going in some direction and it was electron in some shell here, and then here gamma ray is completely absorbed, electron is emitted in certain direction from initial direction with theta. Electron has got velocity say, mass of electron say m, velocity say ve. So mve momentum of electron is mve, linear momentum. This gamma ray has got E is equal to h nu. Gamma ray has got energy, has got momentum. The momentum of gamma ray is given to momentum of this, and this electron has no preferred direction. Emitted electron can go in any direction. So this will have now linear momentum component, one component in this direction, that is the x component Ve cos theta, and this will have another component on this direction, say m, that is Pe sin theta. So this theta will vary because electron has no preferred direction. It can go initial direction, it can go any direction. There is no preferred. Why it should go only in the say zero angle? It can go in any direction. It has got momentum. So this goes to say theta direction. It has got two component momentum. This P cos theta, the horizontal component of momentum is balanced by gamma ray momentum. So momentum of this gamma ray is taken by this electron. And if it is going only in the horizontal direction, the horizontal momentum given to this, no problem. Otherwise, horizontal component of gamma ray, horizontal component of momentum of electron, that is P cos theta, is balanced by gamma ray momentum. What matters about the vertical? How the conservation law is obeyed? Because vertical momentum, it can have any value when theta varies. So vertical momentum, where it will go? Where this momentum will go? P sin theta will change with the theta angle. So where this P sin theta? Who will take this? How the conservation law will be obeyed? The initial momentum must be equal to final momentum. Final momentum are two directions. If it is only theta 0, no problem. It means this momentum should be conserved, should be taken by somebody. And hence, photoelectric effect with free electron is never possible because this momentum is not conserved. So to receive this momentum, there must be another body sitting to take the recoil. Means this nucleus is here, this will receive the recoil, this momentum, and heavy nucleus will receive this momentum and will recoil by a certain very, very small distance because nucleus is very heavy. So the vertical component is taken by recoiling nucleus, or that is atom. So to conserve this momentum, there should be somebody, another body. So photoelectric effect is not possible only in the gamma ray electron. There should be another or third party, third system which will say recoil. And if the electron is outermost, this electron, this will have least binding energy and this will have most tightly bound. So recoil will be maximum here, recoil will be very small here. It means to receive the recoiling moment, we need a third body, another body to receive the recoiling, to receive the vertical component of electron moment. There should be another body where electron is tightly bound, where electron is most tightly bound. If most tightly bound, if your friend is keeping a close hand on you, tightly bound, and another person comes, pushes you, you will not be distressed because you are tightly bound. If it is free, then you will go. So, if the electron is tightly bound, the nucleus will get the recoil. If it is free, the recoil will not come to the nucleus. Therefore, to conserve the vertical momentum of the electron must be tightly bound, and K shell electron is most tightly bound. K-Chaubey electron is most tightly bound, and hence nucleus receives the required momentum. And momentum conservation law Y component is possible. It is not possible with the free electron. That is why the gamma ray interaction, that is the photoelectric effect, is with most tightly bound electron. It is not with the free electron. If it is a free electron, it becomes another effect, and that is the Compton effect. So I will talk about the Compton effect and pair production and how to use all the three effects for gamma ray detection in the next lecture. So I stop today here.